Great. Well, thanks so much for having me, guys. Really appreciate it. Let me know if you have any questions along the way here. We can stop anytime, and I can go overtime here if some folks want to stay on for a longer discussion, if necessary or wanted. Right. So I'm Alec Engel. I've been in the solar physics community since 2005, 2006-ish. Have always been interested in data-driven insights, and really a data scientist for the past 10 years, more or less. Jack Ireland actually is on the Telecon here. He got me interested in sort of automatic CV type of stuff back when I was just a young lad. And I know Nick Murphy from the CFA. So hi, Nick. It's been about a decade. Good to see you. So crazy. It's nice to see this community. And Joe Plowman, good to see another MSU person here, not to be confused with Michigan, of course, the real MSU, Montana. Right. So I work at NextGen Federal Systems. What I'd like to impress upon you on that, and what I think dovetails nicely in terms of what we bring as a company, is that we're an enterprise IT company. We develop cloud platforms, architectures, modernization, so they work on AWS GovCloud, AWS Cloud, Cloud One platform, different DoD platforms. So that's what we excel at, is really making sure that there's modernization in your technologies. And we do a lot of supporting for the Department of Defense, so Air Force, Navy, and things like that. So just some high-level accolades. I'll just flash this up so it's recorded. If you want, you can go back and hit the pause button if you're curious. But yay, NextGen, we're really, really great. So here's what we do, some of the solutions and research development. I mainly live in the research and development area of NextGen, where we do machine learning, space weather forecasting, soil moisture analysis, some drone stuff and things like that. But of course, why we're here today is Sprints. And Sprints was born out of a 2016 NASA STTR, which was aiming at extending the forecast of solar energetic particles. And that's the main thrust in terms of a research topic that Sprints is driving towards. However, I think it is the overall technology that is wrapped around this approach for better forecasting for SEPs that's probably of greater interest for the community here. And hopefully I get that point across. So some of the key takeaways here. So to the blue box, it's an ecosystem for collaborative and repeatable space weather data processes, science, and forecasting. So how do we start off on this endeavor? Well, we built up AWS GovCloud, can be deployed in multiple ways, containerized, things like that. I'm a big fan of machine learning and data-driven insights, so I want to start with the data sets that are foundational to our community. And so these are, at least in my book, the GOES, X-rays, protons, electrons, and the solar wind data. So that's what we started to database. And by the way, our team is comprised of myself, mainly a data scientist with expertise in the field of space weather, but we also have data engineer and a machine learning expert, actually a couple of them now, and also a couple of folks who can really do app development in terms of, hey, what kind of tools do you want to develop out of this capability? So timescale DB, REST APIs for machine-to-machine processes, because a lot of our customers are interested in that. Hey, we don't want a forecaster in the loop. We just want you to give us a probability with a confidence level on your forecast, and we're going to feed it into this other machine. We have Python APIs.
I'm going to have to jump off in a minute. Oh,
yes.
Sorry, Alec. I'm going to have to jump off in a minute, but boy, I would love to talk to you about this REST API thing, because that's what I've been working on, is for time series data, like some of the stuff you're describing here, that the happy mechanism. So
yeah, absolutely. Yeah.
Just I'll probably email you separately.
Shoot me an email. Yeah, please.
Great.
And our main development environment is Jupyter Hub. We have experience in using the littlest Jupyter Hub and also the regular Jupyter Hub, and going through the the rigmarole of doing Red Hat and all this Linux stuff. So again, outside of my bailiwick for sure, as more of a data scientist, but that's why you work with a team of engineers, so you don't have to worry about that stuff. Um, so we have catalogs in there. In what really bothers me about this field, heliophysics, I would say the most is our inability, or so far our lack of ability, to have an associated catalog. Solar flares associated to SEPs, associated to radio bursts, type 2, type 3, associated to shocks, associated to CMEs. I understand that there are catalogs out there, but we're really not coordinated at all. And so I'd like to see our community become coordinated in that. And what we tried to develop here, I think, is that initial step in that direction. And then the ability to data fuse and set up your data pipeline so you can be machine learn ready, as you guys previously discussed. And then also it was mentioned in the previous discussion on how nice it would be to have a single environment that has all these wonderful heliophysics focused packages, which we currently have. So we have SunPy, Komodo. You saw a demonstration of that last week or a couple weeks ago. And then, of course, SpacePy, PlasmaPy, SapPy, and then the ability to link into CCMC APIs and also use the SunPy APIs. If it's out there, we just basically want to create hooks into those types of capabilities. We're not looking to replace anything. We're looking to coordinate everything that's useful for this community. All right, so those are the takeaways. And I just have a few more slides here. So to focus in again on the sprints application, it was to forecast SEPs. And that's a reason why we picked the data sets we were picking as well. Other than that, they're foundational. But pretty aggressive forecasting requirements here coming out of AFRL. There are 5 different requirements, your typical 10 MeV, 10 PFU, if you're familiar for the S1 through S5 radiation scales from NOAA. That's this guy here, but moreover, they're looking for the 6-hour temporal resolution as opposed to, hey, we're expecting an SEP event. What's the threshold of that SEP expected to be? That's for the entire SEP event. So we're actually interested in doing that every 6 hours throughout the SEP event as opposed to the entire SEP event. So it's a good challenge, and I think I might have some results if folks are curious. But again, the bigger picture is the ecosystem that was built around this particular forecasting application for which we got funding. So let's go ahead. This is the main tool I'm going to be demonstrating to you guys. The thing I really love about working in these Python ecosystems is you can do the whole research to operations, operations to research, pretty much using the Jupyter Hub, and as long as you have the engineering to support it, there's a lot of capability there. So this is pure Python using Bokeh. This graph plot here, actually you have the ability to view all the data from 1986 through present. You have the detections of the different flare events. You have the ability to say this flare was associated to this SEP event, was associated to this shock and this CME. And then that actually edits the metadata in the database. So really using a UI type of tool, which I think you really need to, especially when you're trying to determine, hey, is the start time of this event accurate? Is the end time accurate? And things like that. And really, once you have the start and end times of these events, and then you're able to associate to each other, then you just need an algorithm or some sort of code like, hey, I'm interested in this metadata. So for instance, a lot of folks say the peak ratio of the long and the short X-ray channels is a really good metadata type to investigate to see if it can forecast accurately the SEP profile or some sort of attribute of the SEP event. So you just click of a button, you execute your Python notebook cell, and then for the entire database, you have a new metadata parameter calculated, and it's a new column in your data frame, and boom, you're ready to hit a button, and now your machine learning model sets up the training, creating the forecast, and gives you the skill scores right in a matrix, all in under about an hour or so. So as soon as you have a new metadata type, you're good to go, as long as your database supports it. So sort of the bigger pictures in terms of the foundational tools in terms of visualizations, I guess you could say, that are coming out of this project are the ones, the top left I just showed you, where again you can put in multiple types of forecasts coming in. You can put in NOAA SWPC 3-day, you can put in MAG4, you can put in CCMC forecasts for models there, and you can see how they all compare against each other, as long as you're not doing too much at once in terms of visualizing them. But it's always nice to see historically how some of these models do, understanding the cadence that they put out, and things like that. So it's always good to visualize historically how a model does, forecasting wise, and so that's why we want to implement something like this. On the top right is something that we hope to really get on, is using Xarray and Dask to get some of these files a little bit more organized in terms of the heliophysics data holdings. Also a discussion that was hit on a little bit earlier. So we have a lot of experience working with geospatial data in this area, working with Xarray and Dask and chunking and all of that stuff. And we've built platforms that are able to screen through terabytes and terabytes of data and analyze it on the fly. And so, yes, I think this is something that should be looked at in the future, in the near future. This is all possible today or yesterday, in my opinion. But certainly some of the packages in the past couple years have only just made it possible. So it's still cutting edge.
Is that
So,
related to Helio Viewer? Speaking of Jack Ireland?
yeah, I definitely know Helio Viewer. Absolutely useful tool, great tool. I got it on my desktop. This is different than Helio Viewer in that you actually analyze the data itself. And maybe I should be careful what I say in terms of analysis. But as far as I understand, you're analyzing the scientific data, not JPEG 2000s. It's been a while since I've done a revisit of what Helio Viewer does, to be honest. But Helio Viewer still, is great for screening through lots of data as well. The idea behind this is be able to screen through lots of data, but do scientific analysis. And again,
I think
feel free to.
that is beyond what Helio Viewer does.
Right.
Yeah,
Yeah, go
Helio
ahead,
Viewer
Jack.
is, sorry, Alec. Yeah, Helio Viewer is, designed to be a visualization tool. So this is pretty different. So analysis is different. So that's why we use JPEG 2000 files, because they're small. They're much smaller than the FITS data. So we're able to stream them and store them and with a much smaller footprint. So yeah, it's kind of very different intentions. Yeah, that's it.
Yeah, I view them as sort of a side-by-side capability for sure. Like if you're doing an exploration, you want the Helio Viewer, but if you're interested in this active region between these days and those days, there should be no reason why you can't have all of AIA and HMI in literally a single netcdf file, which might be definitely terabytes in size, but you should be able to screen through that no problem. A brief aside, with the concern of diluting this demo, but we've done this. I mentioned we did it for geospatial data sets. So we did it for soil moisture. We were doing machine learning for soil moisture. So this is a pre-recorded demo, but I just want to give you a flavor of some of the other capabilities that you can do. So here, for instance, you're looking at about 500 gigabytes of data from the SMAP, NASA SMAP mission, which is soil moisture. You're able to go through it very quickly, and create these dashboards, which make it really easy to interrogate the data and also just do analysis on it. So, and you can create dashboards. So let's get rid of all that ugly code. say you have a user in the Python community, whether it's heliophysics or geospatial or soil moisture, they don't want to see all that code, so they'd rather just use the tool, and basically they use it in the way that you have the tools set up. So this particular one here is just a nice map of the SMAP level 4 data going from 2016 to present. You have the ability to view in situ stations, and you can see the bokeh tools on the right. You can do a region select, and based on that region selection, another submap will be drawn. So here's an area in Texas, and that's an area we focused on to do machine learning. So layers and layers of geospatial data thrown into a neural network to try to predict the SMAP level 4 data. And here you can see some of the visualizations that we had. So this is using the soil grids data set, absolute depth to bedrock, bulk density in the middle, and then a nice data shader scatter plot there. Data shader is great when you want to visualize billions of points against each other in the scatter plot. And this soil grids data is high resolution. I think it's on the order of like 20 meters or something. So it's very, very high. So you can create all these tools and there's no code that a person needs to see. So you can imagine that, for instance, you're looking at AIA, SDO data, DKIST data that's in this nice NetCDF or ZAR format. ZAR has some potential there to be improved. And of course, when you're doing this, you do have to keep in mind that you are in some cases more than doubling the data volume, at least for your targeted data sets when you do that data translation. So something the field should be aware of as we look at how to modernize things. So anyways, you can create all these wonderful dashboards in the Jupyter Hub, launch them directly into a URL, and the community can hit them and use them to their own degree. You could have a download button. Like, I want to select one of these regions here and say, hey, that's an active region location, or that's a sharp HMI active region patch, and I want to be able to download just the data from that location. So there are lots of ways to tool this capability up. This example here just really quickly shows the importance of data interrogation, because you can see bad data in Mexico and Canada. You see those circles there? That's not good. So you definitely don't want to put that layer in your machine learned model. The chances of you seeing that visualized on the output product of the machine learned model when you're already putting 10 to 20 layers in there is probably pretty small. But anyways, I'm a big fan of data interrogation. Using X-ray and DASK to come full circle is really a driving point. I think this community should go. And I've been seeing a lot of abstracts recently on that. But getting the world coordinate systems into X-ray is a critical point, I think, for this community to go for, and hopefully an opportunity will be there. So forgive me for the brief aside on the geospatial stuff, but we definitely have a better demonstration in terms of the power behind it. So with these notebooks that I've shown you very briefly, you can go through terabytes and terabytes of data and analyze them while going through them. Okay, so back to this guy, just all the different tools you can make from bokeh and whatnot in terms of making your, again, R to O to R ecosystem more coupled and things like that. So I'll keep going here. This is where we're at in the project, logistics. And then if you guys want to see what really we have in mind for the architecture for this community, it's this. So it's Monday morning and we're looking at an architecture diagram, so forgive me, but this is really the way I think we could move about. So your typical ETL on the left, different adapters leveraging what SunPy has already, reaching out and hooking into all these different APIs that also exist, whether it's VSO, Sharps, HEC, CCMC, runs on request, what have you. And then you have sort of your foundational data sets, maybe in your timescale database here, like your X-ray, protons, electrons, and things like that. maybe this community here, let's say it's just the 20 of us, and this is set up for us. So each of us have an allocated 50 gigabytes of data on our data cache, and we're able to download data. So when we revisit our hub or our Python notebook, we have immediate access to it in the cloud. And then you have your Python API that reaches into either other API and adapts to them, or directly to your time series database. And then this is where all the wonderful magic happens of your own analysis, what you want to do, serving up your own tools using the Bokeh server, going through data fusion and those typical processes. And then, of course, this whole hub environment, and ignore the name Swordfish. This was for a proposal, which didn't get funded. But we're gonna press this idea and basically say sprints is the kernel in which we're going to grow this application out of. So just think of everything as sprints. We named it Swordfish because CCMC is a zoo. And so here you have all your different libraries. There's no worry. Everything's built and ready to go. So we got Komodo, HelioFuse, GeoViews, Pandas, SpacePy, SatPy, SunPy, all ready to go. And what's moreover is that directly from a terminal in this Jupyter Hub environment, you can do pull requests right to your Bitbucket or GitHub repo. And then, of course, the idea is that this, again, emphasis unites the research to operations, operations to research community. And I think if you drive that point home, we'll have better success because that's been a big challenge for the field for sure. And then finally here, last slide, I promise. We already support some of the NASA ROSE's O to R teams on here, using it to varying degrees. A lot of folks are interested in the catalogs that we're trying to put together, the associated catalogs between flares and SEPs. And we're just trying to grow the community right now in terms of folks that can have access. We are limited because this is just a funded STTR phase 2 project right now. You can see some of our targeted users, especially in terms of forecasting and things like that, and the research to operations type deal are the top 3 here. But also we've had interested folks from upcoming SMEX missions in terms of, hey, can sprints be the platform in which we provide the SMEX mission data to? And so we can enable researchers to actually go in and analyze data through a type of hub as opposed to just a data repository. So can we provide an environment where they can do analysis with the data and really only move data when they would like to, for instance, to their local or things like that. Then, of course, there are other communities like this community, HelioML, FDL, and I envision all these communities basically feeding in something like sprints and really becoming the foundation and backbone for this R to O to R between these different agencies, right? So that's the big picture, guys. That's what I got for you, and that's what I have for slides, and then the rest of it is just a Jupyter Hub demonstration. So I'll pause here for any comments or questions or discussion, and I'll just transition over onto the web here. All right, if nothing, this is the tool. Hopefully it didn't time me out. It doesn't look like it did. So this is a Bokeh tool, again, using our database for X-rays, protons, and solar wind data. And it's pretty reactive, right? You can get through 1986 through present by stepping 8 days at a time, probably in under 3 or 4 hours. So it's pretty quick. If you really want to get familiar with all the events from 1986 through present, we do have the capability of going before that, but we just started at 1986 in terms of data reliability, and there were some data spikes earlier on. But here you can see some of the identified start and end times of the SEP events, start and end times of the flare events. If I go ahead and click on, what's a good event to click on here? I want to click on, so the data table on the right, you can edit this table. So for instance, if you think the latitude longitude is incorrect, or the NOAA active region is incorrect based on the flare you're looking at. So this flare right here, I just selected number 23 with an ID in the database here. You can see that I have this flare being associated to this SEP event. So I want to take a closer in look. It looks like I already corrected the start time of this SEP event. And you could probably argue with me that like, hey, I think it's probably 5 minutes later or something like that. And in that case, you would go to the right here, and instead of 1750, you would just click on that data table, put a 5 there, and then click Update Catalog. And if you pay close attention to the plot, you'll see that change slightly. So it just bumped it over a little bit there in terms of where it was, where the start time was. Right, so that's pretty much this tool. And right now we're getting the ability to visualize the different forecasts and the forecast panels that we have here. We're displaying Mag4 and things like that, and some of our own forecasts that we've developed. And so we view this tool as sort of a one-stop shop, and it's your very typical space weather tool, right? I think Lockheed has a tool, NOAA SWPC has a tool like this, but I've never really seen a tool where you can go from your whole data repository of flares, SEPs, and solar wind data, and you can actually interrogate the data, take a look at it, and things like that. So I just think looking at the data is such a key thing for you know, any type of science really in general, but especially when you're looking at this stuff. So any questions on this guy here? This is sort of our main tool that's come out of the project. But again, there's no limitation. If an operator or a scientist sees like, hey, I'd really like it to be this way. Well, it's all in Python. So go for it. Create your own version of this tool, or just go ahead and create something totally different with the data sets that you have access to. So any questions on this tool, this time series tool? All right, good deal. All right, so one of the another aspects of it, well, I guess I can just show you. So this is what your home page looks like. If you go into shared, you have free floating data. So a lot of this free floating data is what's not in the database. It's like CSVs of type 2, type 3 radio bursts and things like that. But those can just be read in just as easily as the database. Just, you know, a Python data frame or CSV to Python data frame will do it. And then you can go fusing from there, fusing your data from your database, whether it's a flare, catalog, ID number to a type 2 radio burst type of thing. So anyways, this location again is free floating data. So in the notebooks, you can see the different team, all the team folks that we have on here. In my notebook here, which is a god-awful mess, I need to organize it a little bit, but I have a couple of projects I'm looking at. This was work done by one of our interns to create a 3D visualization of CME. So this is just using plot LY. This is for the May 15th CME of 2005. For me personally, I think predicting BZ is great. But I think we should also take a look to see if we can predict helicity as these structures pass by Earth. So that's the main thing that we're looking at here for this tool. We want to see if we can quantify the rate of change of these structures as they go by and things like that. So what was the rotation? Was it pi? What was it? And just collect another metadata column for us to potentially use and just throw a machine learning model at. All right, and then over here, I'll leave a few minutes here at the end here, so this will be the last thing to demonstrate. I guess these are the skill scores. So this is a create training data notebook. So with all those start and end times of the SEPs that we have and the associated catalog, and knowing those AFRL requirements that we have, those 5 of them, well, let's create a whole data frame that is ready to be trained on. And basically that's what this column here does. And at the end of it, this is these are your events here. So you have 221 flares that are associated to SEPs. And then after some cleaning, you reduce that number a little bit, and then you process the flares only. You create your training testing splits, get your proton values for them. And you can see there are quite a few of them here. There's 151,000 into the requirements that we're looking at. Again, the different SEP channels here. So 1 MeV, 10 MeV up to 100 MeV. And then calculate the labels based on our requirements. So again, very much a regimented rinse and repeat type of process. And when I go in there or somebody else goes in there and changes a longitude, changes a start end time of that associated catalog, that gets propagated into the database. So as soon as Brianna, who's our machine learning expert, as soon as she runs this notebook, that's there for her, that corrected event. And then we can see how those skill scores change and things like that. So didn't want to give you too much code here, but again, just to give you the general flavor from a data-driven machine learning project on how we're leveraging these types of ecosystems, which I think is generally the picture we're all after and discussing here today. So I'll stop there and give us a whole 4 minutes here to discuss, and I can answer questions. So thanks for the time, and I can leave up the screen in case there's any questions too. So.
I have a question, Alec.
Yeah, Jack.
Yeah, so you mentioned something about X-ray and world coordinate systems.
World coordinate systems?
Yeah, and X-ray.
And DASC, yeah.
Yeah,
X-ray in particular, yeah.
Can you speak a little bit more? Can you say a little bit more about that?
Yeah, broadly, right now the community has a specific package called ND Cube, which basically takes care of a lot of what X-ray would do. However, X-ray is more of a it's a more focused development product with support from Anaconda. And basically what we'd like to see, I was talking to some folks at Anaconda, is have X-ray support the world coordinate system. Because right now it works for geospatial, right? I gave you that demonstration of geospatial data, and that's working properly with X-ray and DASC. But as of right now, at least in the formal release of X-ray, and people might have their own GitHub repos that have taken this into account, X-ray does not have that capability to work with the world coordinate system. But as soon as it does, then you can translate, all your FITS AIA files that you want into NetCDF, and then X-ray will just read in that NetCDF file or multiple files if you have them, depending on how you organize them, and be able to display them through DASC and other methods properly. So that's very high level there. I'm not too in tune with. I've talked to. I know you were on the email chain, but I've talked to who's Paul, or no? What's his name from SunPy working in DKIST now. But there's a lot of interest, and we'll see if we can capitalize on actually getting it implemented in X-ray, because right now they're looking at. The X-ray team is asking the question, do we have all the coordinate systems that we'd like moving forward? And the quick answer is no. And so they're looking for community engagement on how to address that right now.
Okay, you might want to suggest that to the SunPy people to jump in on those discussions. So I think they would be interested in that. So.
Yep, I will. Yeah, it's on my list to get a little more organized on that. But yes, I will for sure. I'll keep you in the loop too.
And possibly AstroPy as well, actually. So because the SunPy coordinate systems just sit on top of AstroPy. So.
Right, gotcha. Yep, understood.
I can ask you another question if nobody else is. What was your concept for the, you mentioned sprints and NASA SMEX. So you would put the SMEX data into like AWS, and then sprints would just provide like an instant interface to
Yeah.
it. So
Yeah,
they'd be
exactly.
like,
Yeah.
okay, could you also use sprints as part of a SOC?
It's a good question. I'd have to get my data engineer on here. I don't see why not. Um, it might be a slightly different component. But yeah, I could see it fitting in for sure. Yeah. And for the heliophysics mission, I think the idea is that, you know, if this were to happen, we would work with that team and say, hey, what kind of interface are you guys looking at for access to your data and or analysis to your data? And what does
Right.
it look like and feel like? And then we would work with them and design it. And hopefully that would take care of, you know, in an ideal world, 70% of a user's need. And then the remaining 30%, a user might develop their own widget or UI to view that mission data, or they might download that mission data because they're still only working in IDL and they'd rather just download the data locally and things like that. So providing that sort of flexibility, but also a foundational set of tools to access and analyze the data would be the approach, and it would depend on mission to mission, whether it was imagery combined with in situ, what have you.
Okay. Thanks.
Yep, you bet. I'll stop sharing there. I did talk about this with a little bit with Aaron, and I met with Jim Spann a couple of weeks ago, and I think I got the point across to him, and he sort of came out and said as well that this has the potential of being a R to O to R virtual center of excellence. So I don't know if you guys have heard that terminology thrown around, not thrown around, but given out by the community, like folks like NSF and things like that. And of course, I'm all for that. That's why I'm excited about the tooling of sprints, is because it's meant to be used in that sort of fashion. And so you can imagine a Dockerized sprints sitting at CCMC, containerized at SWPC, containerized one for this team maybe, for all the different communities, containerized for and deployed at Air Force. And basically you have the mechanisms in there. So when, for instance, somebody comes up with a better SEP prediction capability or whatever, it's tested at the CCMC through their test bed, and then it's propagated to NOAA SWPC, and then it's tested at their test bed, and then hopefully eventually translated over into operations. So creating that connection a little bit more functionally across a virtual O to R, R to O center. And I know I'm not the only one thinking along these lines, especially based on the discussion that kicked off today's meeting. So I think it's really exciting that we're all thinking along the same lines. And my opinion is stronger together. If we can come up with a framework that can collect us all, that's sort of ideal. So we're not sort of working on this ecosystem, this platform, and that one, but we want to have a unified capability, but at the same time, understand that resources are finite, and we want to make sure that we can be inclusive. So just another additional note.
Sounds good.
Yep. Well, thanks for letting me demo here. Just shoot me an email if you guys have any questions. I'll be popping on these phone calls probably occasionally here. I'm off for most of May, but I have this on repeat on my calendar, so I'll be joining for sure. So thank you.
Thanks, Alec.